Welcome. Third day of the week. Today's speaker is Herman Verlinde. I don't think he needs an introduction.
Okay. Thank you for the kind introduction. And thank you for the invitation. Again, it's a pleasure to be here. This is actually my first time here at the GGI. It's been a long-term plan to make it here. Finally, I did. It's also a pleasure to at least to be talking about work recently done with these collaborators. Again, every time I feel guilty that this should be hopefully published soon, but with this summer, again, it's work with Ahmet and others. And in the second half, I'll talk about sort of some ideas where it applies to the state of a Hawking pair. Now, if you think about the black hole information paradox, one way of summarizing the information paradox is that the Hawking pair is created out of a vacuum, and therefore it can only carry the quantum numbers of the vacuum, and therefore it doesn't contain any actual information. In two ways. One, it's that it's sort of, it looks quote unquote thermal, and secondly, it's actually kind of in an entangled state, and the entangled pair is in a given state, and therefore it doesn't contain any quantum information. Nonetheless, if you detect a Hawking particle, one is supposed to be able to extract information from the state of the black hole, because the black hole reduces its entropy. That quantum information has to go somewhere. So there's an actual paradox between, of course, a tension between the two. And the tension is kind of a time-dependent tension, because if you look at the Hawking pair as it is close to the black hole horizon, most likely it's actually really a vacuum excitation. It hasn't had yet time to interact with the microstates of the black hole in a way where a particle that sits just right outside of the horizon will not tell you much about the microstate of the black hole. It's a virtual pair. Whereas if the particle reaches asymptotic infinity, at that point it really will reduce the energy of the black hole, and therefore it should be reducing the entropy of the black hole. So there has to be some kind of transition, and some people have been asking, hey, there must be a moment where this information is being transferred. And part of the point of this talk is actually that there's a pretty sharp way for us to now determine when, not so much how, but at least when this information transfer happens. And the answer is kind of hidden in these pictures. It turns out that if you look at a Hawking pair and you do the computation of the Rayleigh entropy of a Hawking pair, you have to do basically, you can, in first approximation, a free field computation. There are going to be Wick contractions involved. And if the Hawking pair is close to the black hole horizon, it turns out that the Wick contraction that dominates is between the Hawking particle and its partner. And that's the moment where, at least that's the regime where the Hawking pair is still in a uniquely entangled state. But at some point, there's going to be another Wick contraction in the replica calculation, where the Hawking particle is going to be Wick contracting with other things that are sitting on another replica. And that's the moment where the information is starting to come out. And semi-classically, we'll be able to compute how much information comes out simply by looking at the saddle point configuration. That's the summary. If you don't remember anything else, these two pictures are the things I want you to remember from this talk. So the discussion will start actually just with ADS CFT, and actually we'll do some discussion of operator product expansions in conformal field theory, which will provide some of the intuition for this. Yes.
You said you'll explain when it starts having information, not necessarily how it gets it, right?
Not how it gets it, but indeed how much it's.
Summary, you seem to indicate the opposite. I'm confused. Did you tell us when it starts having the information?
Yeah. So I can tell you where.
And what's the summary?
The summary is that it's going to be basically. It will become clear from this picture, but it will be at the moment where the Wick contraction jumps from here to there, and the jump will take place when one propagator becomes shorter than the other.
Is there a way of phrasing this in terms of like where the Hawking particle is when this happens?
Right, because basically, and I'll explain that in the first part of the talk, is that here I'm drawing a thermal circle. Actually, some of Hawking partners are basically particles sitting on the boundary of an ADS space. But actually, there's a dictionary between the boundary of ADS and where it sits on a spatial slice. So I'll explain that. So there's going to be sort of two. Basically, it's a semi-classical calculation. But again, in terms of words, if you would have not, even before my talk, or even Hawking at the time might have given you the following answer. If I ask how much information does a Hawking particle contain, basically the computation would be take the Hawking particle, detect it, at least basically extract it from the state, and then see by how much the area of the horizon is being decreased. That's the amount of information that it has extracted from the black hole. But that's in the end going to be the answer, but it has a very interesting kind of non-trivial dependence on the distance from the particle from the black hole, which I'll be able to compute. We're going to start sort of microscopically, and we're going to think about ADS CFT. And there, to some extent, at least, black holes are just basically heavy excited states in the CFT. Using the operator state correspondence, you can think about it as that the black hole is being created by a heavy operator on the vacuum. And again, this is sort of through radial quantization, you can connect these two. Often actually, looking at a pure state is a bit of an idealization. It's actually better to think about an ensemble. You can take the microcanonical state, which actually is my favorite one, where you fix kind of the energy of the state, but not completely exactly, but you sum over states all in the neighborhood of a small energy window. Or you can look at the corresponding thermal ensemble, and I'll be looking at all three during this talk. And as I said, this thing basically represents in the bulk some kind of black hole state, but the black hole has an interior and exterior. And typically we talk about things like an entanglement wedge, where from the point of view of the boundary, which is sitting on the right, I can only kind of, let's see if this works, yeah, see this region. I'm going to be interested also in what happens in this interior region. I'm not going to be talking too much about this interior region. I'm talking about this other region here. But if I can access this region, I can also make it up here just simply by propagation. But the key feature, of course, that most of us are familiar with is that time, at least the Schwarzschild time, goes up here, but it actually goes down here. So even if there's not a two-sided geometry, because here I'm going to be thinking about a one-sided state, there's some kind of end of the world feature here. There's going to be some interior region where time flows backwards. And what it means is that if I put a particle with a given mass here, it will actually decrease the energy of the state. And that's a feature that we're going to be also exhibiting in the, I should do this thing, in the CFT. And the way to see that is simply by looking at the operator product expansion between a light operator and a heavy operator in the CFT. This is the operator product expansion. And these are the operator product coefficients. And here I'm going to ignore spin. I could include it in my equations, but it just makes the equation slightly longer. There's the scaling behavior here, which is determined by by conformal invariance. And what you can do is you can ask, what's the typical energy of the thing on the right, given the two parameters here, h and the energy, but also as a function of the distance. And it's quite easy to see because of this E minus E prime that sits here, that if Z is very large, if the operator is far away, that the thing on the right will be dominated by the energies E prime that are bigger than E. But if Z gets small, then E prime is going to be typically smaller than E. So there's going to be actually, if you just statistically look at this OPE expansion, be a critical radius where the OPE will actually transition from increasing the energy to decreasing the energy. That's an important feature in conformal field theories, and that critical radius is essentially an avatar of the black hole horizon, which I'll explain in a second. So this is the picture. This is the critical radius in radial quantization. Sorry, and basically just on the complex plane. And if the operator is here, it will increase the energy. If the operator is going to be here, it will decrease the energy. And I claim that this is sort of the region that corresponds to the behind the horizon region in the black hole, because decreasing the energy means that there's a corresponding particle that's being created here that somehow manages to decrease the energy of the black hole. And the only way it can do that if it's inside of the red region of the black hole geometry. Are there questions about this? That's an intuitive statement, but it's, yeah, right. The CFT statement is pretty clear. The holographic intuition I'll explain in the next slide. Yes.
Yeah, actually, it's the question. So, what about the descendants?
Sorry.
What about the descendants from the primary?
The dependence on the primary.
Yeah, the
Descendants. Now, so here we're in the black hole regime, or in the Cardi regime, and then if you look at a given energy level in the Cardi regime, the spectrum is dominated by primary fields. I can include descendants here, but and I'm basically I'm not excluding them from this equation as well. They're actually subdominant in the entropy. So most of the OPEs on the right hand side are primary states.
I actually have a question. So the critical radius, is it something sharp that we could write a formula for, or you're just making a qualitative statement that nearby there is one type of dominance and far away from?
Right. So actually, this idea actually was already stated in a paper I wrote like 8 years ago, and then I tried to do the actual precise calculation doing the saddle point, and I was off by, as usually with my calculations, off by a factor of 2. And then the thing is that we actually know the statistical behavior of these OPE coefficients for holographic CFTs. And then once we did the calculation more carefully, we fixed the factor of 2. And there is actually a precise relationship. So there's a precise equation. And from so the different ways of determining that critical radius. One way is indeed just doing a saddle point computation here using the OPE. The other way is to actually use kind of the Liouville equation as a way of characterizing what these OPE coefficients look like. And then the critical radius is the radius where the induced constant curvature metric associated with this heavy operator has a bottleneck. And that you can compute, and those two things match. Yes. Yeah.
The operator to the left, we muted the operator to the right. This certainly is not the case.
It's a good question. I'll get to that in a bit later. Yeah, thank you. Yeah, it's a good question.
Yeah, I'm still trying to understand the setup a little better. So I thought you have only one CFT, and OE0 is the thing that creates the black hole in
Right.
that CFT.
Right.
So there's no left CFT. There's some kind of
Correct.
interval
Correct.
brain or something on the
Correct. Yeah. So
And-
right.
And then what sets the so OH is going to be somehow the Hawking particle? Or?
The OH is later going to be the Hawking particle, but through a dictionary that I'll explain.
So right now we're just supposed to think
This is just-
about a light operator and what happens when I
Right.
move it across the
Right.
critical radius.
That's right. For now, it's just the CFT observations. An important, let me still go back. An important thing about the observation here that energy goes up or down is that if energy goes up and down, it also means that you actually go from a slightly sort of certain dense spectrum to a slightly more dense spectrum, or maybe a much more dense spectrum. And if the energy goes down, you go to a less dense spectrum because the entropy increases with energy. And what that implies is that this operation here, basically, at least if I restrict it to these energy windows, in this case has to be non-invertible because you go from a bigger space to a smaller space. Whereas here it can be an embedding of this space in here if it's far away. And there's a certain sense in which this is already a toy model for a black hole, because indeed, if I would give you the state on the right-hand side, but I didn't tell you exactly which state I took here. I could have taken an ensemble of states on the left. If E prime is bigger than E, you would be able to decode which operator OH you will be able to recover this expression if I give you the right-hand side, because you will have enough information here to do it. However, if E prime is less than E, so if the operator is too close to the heavy operator, you'll never able to decode this operator given the information that I'm going to give you, because basically I'm giving you a certain amount of information in the red lines over here, but that's not enough to recover which state I started with. So there's a sense in which even in an ordinary CFT, there's an interior of a black hole that this light operator can sort of be disappearing from a quantum information perspective by being too close to a heavy operator. Yes. Matt.
Does the critical radius depend on H?
Barely, only through back reaction.
So in leading order, it doesn't.
Yeah, so in leading order, it does not depend on H.
The definition of that dotted line is whether the expectation value of the energy in that state OE is larger or smaller than in the original state. Is that the definition of the dotted line?
Yeah, the definition of the dotted line is where E prime switches sign. So I'll be able to.
No, that doesn't make sense because E prime on the right side is, it can be larger and smaller than E.
It can do both, but I'm going to, there's a saddle point equation that one can write down.
So the definition is not.
So in terms of expectation.
You mean compared to the original state? Yeah.
Right.
Yeah.
Right. So anyway, this is the black hole space-time. The intuition, as I said before, is actually that time flow changes sign when you go through the horizon. You can make it quantitative. In the case of ADS3, CFT2, this is the BTC black hole geometry, the way I'd like to write it. This is basically a hyperbolic cylinder. That's the spatial slice. And this is the time evolution. And this is the Boltzmann factor. And what I'll be able to do is I'll be able to match the behavior of this delta E minus E prime with this particular Boltzmann factor. This is the Boltzmann factor of the, when I say Boltzmann, Tolman factor. So indeed, when I have a particle with a given mass at a given location from relative to the horizon of the black hole, the actual energy will be increasing by the mass of the particle, if it's at rest, times the Tolman factor. And the Tolman factor can be easily extracted from the CFT. And the intuition, again, is going to be that there's going to be a radial direction in my Euclidean CFT. That radial direction turns out to be, you can map it through radial quantization and the eigenvalue thermalization hypothesis to essentially what you might want to call the thermal time direction, the Euclidean time direction along a thermal circle. And the critical radius that we've been talking about is going to be identified with this point down here that sits at halfway the bottom of the thermal circle. And indeed, the dictionary is that if you take a particle and it sits outside this critical radius, and I look at the expectation value of the state, say the norm of the state, then there's another particle that sits on the CPT conjugate side, and then there's a preferred geodesic that goes from here to there, and therefore there's a certain point on the spatial slice here which is identified, and maybe I should briefly go back. This spatial slice here, of course, halfway the thermal circle is identified with that spatial slice here. So indeed, going to the interior of the black hole is essentially indeed going to be mapped to going to the left-hand side of this thermal circle. And the mapping between the dotted line and this lower half circle is through basically this this geodesic. So I can associate a point on the thermal boundary to a point on the spatial slice just by drawing this geodesic. Are there questions about that? So the critical radius in this picture would be this point down here. If you add the extra circle, which I've suppressed here, this is meaning the phi circle, which I've added back in here. Then basically this is the exponential map. So being here corresponds to being here, and the critical radius is this dotted line here. So the left picture is also Euclidean. And then you can actually go through the interior of the black hole and make it back out again. So that's the dictionary. There are papers by Tagiyanagi and Kanato where a lot of these things have been worked out. So I don't think I've made any particularly new observations here, but this is going to be motivating sort of some follow-up discussions. So this is a way of geometrically mapping things you're doing in the Euclidean CFT to things in the bulk. And the mapping is actually very nicely going to be confirmed in the following way. So we now have a prediction that as a function of this location tau, we should be creating an excitation given by the mass of the corresponding particle times this Tolman factor. And I can relate now the location on the boundary, which is labeled by tau, to a location on this radial direction. Turns out that that's simply a simpler relation like this. And now if you do the following, if you basically try to compute the expectation value of the CFT object, and I'll immediately do that here. So here's what I'm going to do is I'm going to take the energy eigenstate, the microcanonical state of the black hole in the CFT, again with the given energy E. I'm going to create a particle. I write down the corresponding density matrix. This is the state with the black hole with the particle. The partition function is that particular two-point function. That two-point function can be interpreted basically as the absolute value squared of the matrix element. Here it is again. If you use ETH, where I replace, or at least E by beta, then I compute that thing, and it's simply the thermal two-point function. So basically, this object here is the thermal two-point function. And if I now want to know what is the energy difference between E and E prime, the thing that I have to do is I simply have to differentiate this thing with respect to tau and take the corresponding expectation value, because tau brings down the Hamiltonian. And indeed, it's true that if I take, give me a second here. Yeah, let me go here. If I do this computation here, I differentiate with respect to tau, I get this cotangent. And therefore, indeed, the Tolman factor is being reproduced basically by the CFT calculation using the ETH. So what you find then is indeed that there's an energy jump, and that energy jump will depend on the location of the particle. So if you wish, there's this H dependence here in the energy jump, but the critical radius is not dependent on little h. The critical radius is this tau is beta over 4. Let me briefly go to the other questions about this. This is just a geometric mapping, and it's a motivation for the rest of the story. Answering the earlier question, how do you actually determine a sharp value for E prime? The way we've done that as well is by saying, hey, there's this particular object, which is my partition function. I can write it indeed as this thermal expectation value, or I can write it like that. This is the kind of quantity that you would compute if you want to compute the transition probability from E to E prime. that expression looks like this. So now I need to have an expression that I can maximize for given E. I can try to determine what is the maximum value, the place where E prime has the maximal probability. And that's the change in the energy as a function of E prime. And one can get the same answer as that I did with the ETH, just by looking at this expression. That second calculation is actually slightly circular because the way people kind of derive the statistical properties of these OPE coefficients is sort of through ETH or to vacuum block dominance, if you wish. So it's self-consistent. So this is all basically an interesting kind of observation about sort of OPEs, coefficients, or at least OPE expansions and geometry in the bulk. But I want to sort of start using this particular idea to learn something more about bulk reconstruction. And I want to go back to this question of the quantum information in a Hawking pair. And the key point is the following, in this case already, is that if you, as I mentioned, if you reduce the energy, you're also reducing the entropy. So there's an interesting geometric transition that takes place here. If you go from the location outside of the black hole to the location to the interior of the black hole. And let's do the computation that actually quantifies the amount of entropy we're extracting here. Yes. Raphael.
Just so I understand the setup, we're not studying a dynamical process right now. We're comparing different states that we prepare.
Correct.
Correct.
Yeah, so what we're doing here, what we're going to be doing with the Hawking pair is a little bit what Wilson was doing with quark confinement, meaning I'm going to introduce some order parameter that's going to create a Hawking pair by hand. And I'm going to, like Wilson was using the force between quarks using his order parameter, I'm going to be computing the quantum information in the Hawking pair using my order parameter. That's what I'm going to be doing later. So indeed, my particles are going to be in the end associated with these local operators, and I'll be a little bit more explicit later on what the free field theory calculation is that one should compare this with. Yes.
I would have thought that the state that you're preparing without the Hawking particle is already in some sense contains a lot of Hawking radiation, right? Normally,
that's right.
So how should I, so there I would think of it as some black hole that's more
right
in equilibrium with some radiation bouncing off the boundary. How should I think of this extra particle as a modification of that, like relative to that?
Right, yeah. So let me outline what I'm going to do, at least in the next 25 minutes. I'll compute here the entropy as a function of the location of this particle, and then I'm going to look at a pair. When I'm going to look at the state of a pair, one would be able to explicitly compute that there's a finite probability of producing the pair given your vacuum state. There's a matrix element, a non-zero matrix element. So what I'm imagining is that, okay, I'm looking at a black hole which is in the Hawking state, but I'm going to have some conditional information about my state. I say, hey, this happens to be the Hawking state where there's a Hawking pair, a particle here, and its Hawking partner is there. So I'm going to tell you basically where the Hawking pair sits. So I'm going to create a conditional state, and I'm going to ask, what is the entropy of that particular conditional state? It turns out that in free field theory, the Hawking pair does not add any information to the state of the original black hole, because the pair is basically just an entangled pair. But in the holographic calculation, there's going to be a particular amount of information that this pair is going to extract from the black hole.
What I'm confused about is that I would have thought all those pairs are already present in the original state. You
Correct.
don't get to add any more.
I'm not adding more, but I'm doing a conditional. I'm basically saying, well, hey, I know I'm looking at a Hawking state with a particular pair sitting there, which I have to do if I want to be able to say anything about the properties of a Hawking pair. But you have to think about it as being embedded indeed in this second quantized state.
I think this seems to be some very similar to what I've been doing. I think if you just do this pair, and in negative energy thing, we'll lose the information in the sense that the number of states is smaller, so you have negative entropy. But the positive one has a positive entropy. That you have to extract. if you extract as a real Hawking radiation, and that's the way that this original entropy going to negative and positive one goes to the outside.
Yeah.
And then
But so, yeah, so let me just continue because I think I'll be hopefully answering some of the questions. Anyway, so I'm going back and forth a little bit between the geometric picture and expressions of this type because the two indeed are important. Both of them are sort of holographic dual, or at least are dual through holography. Let me still make another comment. The ETH type calculations that people have been doing are connected with configurations where, from the CFT perspective, you have this vacuum block dominance. For example, again, if two operators are close to each other, then the corresponding block that dominates is where they produce indeed the identity operator in the middle, and this is your heavy operator. So this expectation value is indeed the thermal expectation value. That's that one over there. But at some point, when the operator comes too close to the heavy operator, the other channel might want to dominate. And then this might be the sort of the more appropriate channel to look in. And then you can think about this O again as this matrix element between E and E prime. And the key idea that we're going to be doing is we're going to keep track again of this E prime here, and we're going to keep track of how many states are going through this intermediate channel. Okay, and that's basically the idea of the entropy extraction. The entropy extraction is going to be, okay, well, am I going to create a bottleneck at some point by mapping things down here? And then, of course, thermodynamics will tell me as a function of energy and temperature by how much the entropy changes. That's just the first law of thermodynamics. Delta S is just the inverse temperature times the change in energy. And we'll see this sort of coming out of a replica calculation quite explicitly. So this is going to be my formula for the entropy. And I'm first going to apply it to the state with a single particle, and then I'm going to apply it for the state with two particles. So if I define an operator, a matrix C, which is basically the OPE coefficient as a matrix. So this is the OPE coefficient as a matrix, but now just with the brackets already indicated over here, okay? I put the Z dependence in it as well. So there's some matrix C, which basically represents my light operator, but I'm now writing it as a random matrix. It's important, by the way, that these OPE coefficients are indeed complex numbers. They basically are random things. The only thing that we basically know about them is indeed their absolute value squared, averaged over some small energy window. So we know their coarse-grained properties. If I take this operator OO dagger applied to energy to a microcanonical state, I can write that density matrix in this form. Are there any questions about that? Yes? Yep. He was hiding it.
I'm a little bit confused as to how you were able.
Is it on? Is it on or not? Yeah, good.
Just not very loud. But if you in this level, how can you take a random matrix approximation for a light operator? It's not a dense spectrum or something. How?
So the thing that's a dense spectrum is the energy spectrum.
Right. So you said the random matrix is a light operator.
Yeah. So the H index is not random. H is fixed, but it's the EE prime part that's random. So EE prime is the matrix, and that's a random matrix because it's going between black hole states. Now we basically know how to do the replica calculations because basically I just take this expression. Let me briefly go back. I take this expression here, I plug it in there. And then I get something that looks like this, is where I have the matrix inserted many times in the combination CZ dagger. So this is trace row to the n because I gave you the expression for the row. And then essentially what you're going to do here, and that's sort of an approximation, but in an appropriate large n limit, this is sort of a good approximation. You can start doing these Wick contractions. Yes.
I think I missed why the ansatz for rho e on the previous slide. I thought in the microcanonical ensemble, it was just going to be the identity on some window of energies. But
That's
then
right.
You decided to make it CC dagger.
Yeah, but I'm not doing the microcanonical window, but I'm applying the O dagger to it. So it's a little bit. It's this conditional state that my density matrix is going to be the density matrix of a black hole with an additional particle.
Oh, I see. That turns it into this random matrix ensemble.
Correct.
I see.
So the C that's here, you have to think about it as the creation operator of a particle.
Okay.
This, by the way, looks a little bit like what you would want to call a matrix product state. You create particles, but the operators by which you create particles are also matrices on some microphysical state. But anyway, I'm just at this point just doing the straightforward computation. Basically, because of phase coherence, you have these Wick contractions between these random matrices between C dagger and C, and the diagonal dominates in certain channels. But there are off-diagonal terms which can dominate depending on how many off-diagonal terms there are, and that will determine which of these Wick contractions will actually dominate. And by the way, if you indeed then want to keep track of how many states there are in the intermediate channels, that's precisely being determined by the energy that sits in the intermediate channel, because the energy will tell you how many states there are. So there's going to be a geometric transition at the moment that the energy switches from E prime being less than E and from E prime being bigger than E. And that's also when these Wick contractions will switch dominance. So that's again this particular picture. But in this particular case, so we're now just computing the entropy of a black hole with an additional particle. This transition is indeed going to happen basically when the black hole goes from the exterior of the black hole to the interior. Here I'm computing the fourth Rayleigh entropy. Trace rho to the fourth. If the particle sits outside of the black hole, sorry, which is which? This is when it sits outside of the black hole. When it sits outside of the black hole, it wants to Wick contract through a propagator that stays outside of the black hole. That's these Wick contractions. But when it goes through the critical radius, the other Wick contraction starts dominating. And if you look more carefully, maybe I should have had an indication on this thing. The energy of the black hole, and maybe I should go back to the previous slide. I wish I had indicated the energy of the black hole in this. Let me just sort of continue. Is being fixed to be E down here. Yes, good.
I'll let you finish the sentence. Sorry.
Sorry, let me be more precise. The energy of the black hole is fixed to be E here, which means that the semi-classical saddle point here is going to be a black hole with energy E with some particle that sits outside. The semi-classical saddle point here is a black hole which initially had energy E, but it actually is going to have a black hole horizon sitting here with energy E prime. And this geometric transition indeed will tell me that the entropy will indeed start changing. The way that happens in computations is that you compute this particular quantity first in a macrocanonical ensemble, where you basically get the thermal endpoint function. The important thing which will turn out to be very important is because I'm taking the nth Rayleigh entropy, trace rho to the n, we'll have e to the minus little n times beta in the exponent. So this expectation value is taken at inverse temperature, little n times beta. You compute the right-hand side, you got an answer that looks like this, where again the n times beta sits here. And then you plug it into the above expression, and you get a final answer for your entropy that looks like this. Yes.
To check what you've done so far, can I interpret it in the following way? Like if I had a black hole and I have a particle outside of the black hole that's maybe about to fall in, then the energy at infinity includes the energy of the particle, but for the purposes of the entropy, we really only care about the energy of the black hole.
Yeah, exactly.
Good. And then somehow there's some analogous statement of where the particle is sort of a right mover on the inside of the black hole, and it looks like it's decreasing the energy, but we should also compensate for that.
Yeah, so basically indeed, if the particle sits inside, somehow the black hole is not, let me see. Yeah, so then it's a black hole with less mass, then it's a black hole with less mass, and then it's basically a generic black hole. But it was created somehow from a more massive black hole by extracting energy from it. So that's the idea. So here, by the way, I indicated the energies in this formula, which is kind of important. So indeed, if you do the computation in a canonical ensemble of the Rayleigh entropy, you get an answer that looks like this, where as a function of tau, which is the location around the circle, you get an entropy that looks like this. This is precisely what I predicted. It's just the inverse temperature times the change in the energy. But you can actually obtain it through the computation that I had before, basically by plugging this in there, which is a different computation, but you'd simply, of course, find the result that's consistent with the first law of thermodynamics. As Raphael was saying, if you go to the micro-canonical ensemble, then initially you find if the particle is outside, you don't care that the particle it's not adding any entropy because it's just the particle with the black hole. All the entropy is the black hole entropy. So S of E is not changing initially. And then suddenly it starts changing once the particle is inside of the black hole. So this is a very reasonable answer. So here I've computed for you the entropy of a black hole with a particle as a function of the location of the particle. And now I'm going to do the same computation now with the Hawking pair. Okay, unless there are questions. Okay, so let's go to the Hawking pair. Oh yeah, so here's the picture in terms of plots. This is the canonical ensemble computation. As a function of the location, it actually first goes up and then comes down. If you go micro-canonical, you straighten out this thing by requiring that this is your fixed energy thing, and this is your micro-canonical plot.
So from the bulk point of view, you might think that either you're like creating a particle inside the black hole, or maybe that you're creating it like in the left exterior region.
Yeah.
It's maybe hard to say which is more accurate because you're kind of in Euclidean here, but I guess it would be a little surprising if there's a simple CFT operator that creates a particle inside the black hole. So is it consistent with what you've computed to think of that as a creation operator in the left exterior?
Yeah, so that's maybe a discussion we should have later. The question is if effectively where the operator that sits inside the critical radius, if that's really inside of the black hole, or if it's one of these mirror operators that Papadoni, Massa, and Raju are trying to introducing. I think the two things are somewhat related. But there is no other exterior in my game. There is no other exterior. I'm just on one side. But you can still go inside of the black hole, even if you're looking at one side of the black hole, in this sense. There was an end of the world brain. So there's never in this story an other exterior. Although that's a discussion we could introduce later, but I'm not introducing another exterior. I don't need. I'm
really confused now. Because do you mean that you're not introducing another boundary or not another exterior?
Another exterior bounded by an end of the world brain.
Because your picture showed another exterior, it just didn't have the infinity. Like there was a second horizon on the left, and there was some region outside of that, further to the left, and then there was an end of the world brain.
Correct. But there is a region behind the horizon which kind of looks like the other exterior, but it's not reaching all the way to the boundary.
That's fine, but that would still allow for what Ben said to happen, meaning that, you know, you have a particle over in that region, which is contributing negative energy from the point of view of the right.
That's exactly the situation we're considering here. Yeah, that's right. So now let's finally, in our last 10 minutes, 14 minutes, look at the Hawking pair state. So the thing on the top is maybe the thing that you wanted to, that's the thing I'm going to consider from the point of view of the free field theory. So the picture should sort of tell you what I'm doing. I'm taking the Euclidean path integral, Euclidean black hole geometry. I put a free field theory on top of it. The Euclidean black hole geometry just projected onto the RT direction, the radial and time direction. It looks like this over here. I want to create a density matrix. That's the exterior density matrix. And rather than just having the thermal state, which the gray blob represents, the Pac-Man, I'm now going to insert two operators on opposite side of the horizon. One is phi, the other one is phi star. Okay, so this to me is the density matrix of the Hawking state with an additional Hawking pair. In a moment, I'm going to compute for you in the free field theory the von Neumann entropy of this particular state. And what you're going to find is that the von Neumann entropy of this state is identical to the thermal state and the thermal von Neumann entropy. So therefore, the Hawking pair for this free field theory will not create any additional entropy. There may be different ways of thinking about it. One is that it's like that the Hawking pair is in a pure state, or that it doesn't do anything. Nowadays, when we talk about von Neumann algebras, if we do this in free field theory, this is the type 3.1 calculation of the von Neumann algebra calculation, of the von Neumann entropy calculation. And I'll explain what I mean by that in a second. Even in the free field theory calculation, there are going to be different Wick contractions, but somehow the Wick contractions in this case are not going to lead to entropy. The Rayleigh entropy calculation goes the same way as before. And what I meant actually by the fact that I'm doing free field theory calculation means the following, is that if you do free field theory on a given geometry, the geometry looks like this. You basically take a Cardi razor, do a replica computation, and the replica geometry will have an angle excess because basically you take n copies of that geometry where you go around n times, and you basically have to do this replicated boundary condition. And it turns out if you do the free field calculation, which I, in inverted commas, would call Hawking's prediction, then it turns out that if you add up all the Wick contractions that you have to do in order to do that computation, you get an expression that looks like this. Because basically you got these boundary propagators that are the thermal 2-point function. The beta never changes because the angle always is beta. You have different Wick contractions and they add up in this particular way. Depending on whether tau is less than beta over 4 or bigger than beta over 4, one of these terms dominates. When tau is in the neighborhood of beta over 4, then you have to take the sum and take the nth power. Okay. Now, since this is the only place here where n sits, if I compute the entropy using this formula up here, and my expression for the entropy looks like that, I'm going to get 0. Because anything that's proportional to n, which this thing will become, this thing is proportional to n, it will give me 0 for the entropy. By the way, I was excited finding 0. This was one of the things I was initially confused about, because now I'm going to do the holographic calculation and find something that's non-zero, so that's different from Hawking's prediction. So now let's go to the CFT computation, which looks the same, except that I'm not filling it in. This is like the holographic calculation. I'm doing the e to the minus beta h, put my 4 operators there. And these O's are going to be essentially the CFT version of creating the particle phi. And then this normalization is now underneath the thermal 4-point function. And now if I, give me a second here. This is the thermal 4-point function. This is like the microcanonical 4-point function, and I can relate it to in the usual way. Now I'm going to compute again the Rayleigh entropy, essentially in the way we done it before. And again, I'm going to be doing the Wick contractions. And the Wick contractions are again going to be interpreted in terms of these random operators. That's one way of interpreting them, in terms of these random matrices. Or you can interpret them from the bulk perspective, as doing the free field theory in the bulk. Except if you're a little bit more precise now, is that the expectation values that we're going to be computing here are going to be expectation values indeed in the replicated geometry, and therefore the inverse temperature will be little n times the inverse temperature. And the sum over all the Wick contractions will have 2 regimes. One regime, again, where the operators are going to be closer to each other through this Wick contraction, and there will be another regime where the other Wick contraction will dominate. And the important difference between the two, again, is that the energy E, which is the one of my microcanonical ensemble, will be projected to be the energy of this channel here. And indeed, it's basically part of the geometry, and the saddle point will have the entropy of that energy. So the entropy that I'm going to be computing here, and you can do it explicitly, will be the entropy of that energy. Here it's going to be the entropy of E prime, and E prime will be different than E. And again, you can do the computation again with the replica method. Doing the Wick contractions from the bulk perspective, which is sort of the easiest way of doing it, or doing this ETH calculation, you get the following expression. So now the little n is sitting in many more interesting places. First of all, it sits here. This is an expression that's quite familiar in holographic replica calculations. That's just the thermal nth Rayleigh entropy. But now if you have the operator insertions, you also get the 2-point functions, but the 2-point functions are now computed at inverse temperature n times beta. From the point of view of the bulk, it basically means that rather than having a conical deficit, conical excess at that point here, this point here is now going to be a smooth point of this bulk geometry, and requiring smoothness over here will put the little n here. So the difference between the free field calculation and the holographic calculation is that little n. So now you can just do the, compare it with this. Again, here the little n is missing in the free field theory calculation that sits up there. And therefore, if you now compute the Rayleigh entropy from the point of view of the holographic calculation, you get a non-zero answer. And the non-zero answer will be such that actually if the Hawking pair is still close enough to the black hole, it turns out that this particular Wick contraction will still dominate. And that's when the entropy doesn't change of the black hole. But when you're basically getting under 45 degrees, so that's beta over 8. When you get to beta over 8, you go to the other Wick contraction. And that's when you get a non-zero answer. And the non-zero answer turns out to have this particular form. And what you're going to see, and you don't see it on this plot here, initially up as a function of the distance from the black hole, which is the angle theta up there. Initially, the entropy doesn't change. Then it's going to be a critical radius where the entropy is going to linearly basically increase. There's a factor of 2 pi h out front here. When you make it to the boundary of ADS, the amount of entropy that you will have extracted from the black hole will be 2 pi h. That's the total entropy that you will have extracted from the black hole. But here there's a formula that actually tells you how gradually the information is escaping as a function of the distance. Yes.
You probably said this when I missed it, when you switch from one particle to the pair. Are you adding a pair that's in some kind of entangled state analogous to the vacuum, or you are just adding two particles?
It's a good question. So if we talk about Hawking pairs, we often think about them as entangled pairs. And it's true that if a Hawking particle would have a spin, it will be anti-aligned with the partner. So that then in that way, it will be an EPR pair. But if it's a single particle without any quantum numbers, and I project on the state where the particle is there, then there's no longer entanglement with the Hawking partner. The entanglement between a particle and the partner is the entanglement between the state where they're both there and where they're both not there. So it's the particle number that creates the entanglement. Here I'm actually projecting on a state with a given particle number. So by the way, I've not done a computation here that will allow me to determine the complete entanglement between the partner and the particle. So I'm not computing the entanglement between the Hawking pair and itself, the two particles in the Hawking pair. But if it's just a single particle without any quantum numbers, and I project on the one particle number state, then there is no entanglement. But I'll admit, these are more careful questions that one should study, but these are basically free field theory questions.
I'm okay with, having some calculation in some regime where you know what it means.
Right.
But I'm sort of trying to, I'm angling for whether you want me to think of this as some dynamical process where a pair is emitted by the black hole and now it's propagating away from the horizon, and at some point along that dynamics, something happens to the entropy, or is that, am I pushing you into a regime where you don't want to discuss right now?
So if you want me to give a semi-classical interpretation of what's happening here, is that your question? Okay, I can try to give you as good as I can do. Let me say the following. So if we go again briefly to the CFT, the free field theory. So this calculation by itself, hopefully is self-explanatory. Again, I'm preparing through a path integral a particular state. By the way, if you want to basically give this a sort of in modern parlance, the calculation that I'm doing here is that on the next slide, I'm doing this calculation in the CFT where I have OO daggers applied to the CFT. Now, what I could do is in order to compare it with the free field theory calculation, I could say the following. It's okay. Let's look at the operator algebra that creates the bulk QFT. Let's take the strict large N limit of my CFT, where I can strictly do bulk QFT calculation and not include back reaction. Then from the point of view of that operator algebra, the state that I'm looking at looks like this. This is my free QFT bulk calculation. It's not an entangled state between phi and phi star, because if phi is a scalar field without any quantum numbers, then phi and phi star are each a particle that are being created. But I could put an index here. I could put an I here and an I there and sum over I. That would change the calculation somewhat. It's a modified calculation that would add some entropy to this whole system. So this is the computation that I'm comparing with. And the basic claim is that if I compare the free field calculation with the QFT calculation, the difference between the two is precisely summarized in this slide here, that this formula is the free field theory computation, and that formula is the holographic computation. So you can see quite explicitly where the difference goes. And basically, the interpretation of what this thing means in my mind is the following, is that in the microphysical state associated with the particle, so I have a microphysical state and I have a Hawking pair. Knowing the location of the Hawking pair, there are probably many microphysical states that are compatible with a Hawking pair at a given location. Those microphysical states have relative phases, and the quantum information of the state is contained in those relative phases of the microphysical state. And now you can ask, how much quantum information is contained in those microphysical phases in the microphysical state? There's no way of measuring them with any low energy observable. They're just hidden somewhere. But the lesson that we've been learning over the last several years is that if I now start doing a Rayleigh entropy calculation, where I start squaring my wave function, where all those phases eventually can constructively interfere, then gravity will find new saddle points that will take into account those microphysical phases. In this case, the saddle points are just being governed by different classical propagators. Here, my different saddle points are just different Wick contractions plus back reaction. And somehow the gravitational back reaction that will account for the back reaction on the area of the horizon knows about the microphysical phases that are present in the state. So this calculation, I think, precisely quantifies how much quantum information there is in the state. It doesn't tell you literally that the Hawking pair is carrying it. Most likely, the microphysical phases are going to be carried by soft modes that eventually will make it off to infinity. But this quantifies how much information they contain. So that's sort of the best I can come to so yeah, right. So there's no microphysical mechanism that explains what happens here. This only quantifies how much is happening.
Question?
Yeah, further question about your result. So in the second plot, you have the entropy that is decreasing, and then it is negative compared to the thermal entropy of.
Correct. Good question. Yeah.
So what is your explanation for that part?
Yeah. So thank you. Excellent question. So indeed, here I'm actually computing, if you wish, the entropy that's left after I've done my measurement of the Hawking pair. So there's different ways of thinking about this. I'm interpreting, probably I should interpret the state over here. By the way, the intuition, of course, of why the entropy goes down is simply because the O dagger was actually a matrix that lowered the entropy of the state first. Then the O is something that increases the energy, but it doesn't increase the entropy. So there's this bottleneck. I'm thinking about Hawking pair basically as a pump, where the antiparticle that goes in is extracting the information and it's projecting it down. And then the particle that's outside increases the energy again, but without adding the information. So somehow there was entropy lost in this state, but the amount of entropy that's lost in this state, I should think about as basically the amount of quantum information that I'm losing by actually having done the projection on a given state of the Hawking pair. So there was microphysical interpretation that was being information that was being reduced by the measurement. That's why it goes down. And then indeed I have to essentially basically postulate that there's unitarity that tells me that apparently the Hawking pair is associated with quantum information that's contained somewhere in the information in the Hawking pair system. So there's a transfer in that respect. I think I am quantifying the amount of quantum information that's being transferred from the black hole states to the state of the Hawking pair.
create the particle, you're actually having some positive energy, right? And then it should give you some extra entropy when you compare to the black hole entropy.
If I create a particle in a given pure state, I'm not really necessarily adding entropy. It's true that if I would have done the thing that I was mentioning before, if I put an index I on my field phi, and I start summing over an index I that entangles the Hawking pair, then there will be another contribution to my entropy, which I can call the entropy of the Hawking pair itself, at least of that particular degree of freedom of the Hawking pair. But the fact that the entropy goes down is indeed because of the fact that the measurement of the Hawking pair is somehow extracting that information, right?
Thanks.
So I'm a bit confused about the statement of projecting. I mean, aren't you kind of taking the Hartle-Hawking state and then, or whatever, some microcanonical state, and then acting with a pair of field operators? So that might create a pair of particles, or might annihilate particles at those energies, right? You're not actually projecting, are you?
I am projecting. Because the operator C dagger C is a projection operator.
I thought to create C, you took the microcanonical density matrix, for example, and then acted with this field operator on both sides. Right?
Correct. But the
So
C dagger.
New density matrix that you have after acting with the field operator.
Correct. But part of the puzzle is, and again, this was sort of mentioned also in earlier papers during the UMPS discussion, that operators that create particles behind the horizon are projection operators. Because basically they reduce the entropy of the black hole. They go from a bigger space to a smaller space. So the C dagger C is doing this thing. It starts from a state, goes to lower entropy, goes to higher entropy. So it must be a projection operator.
Okay, but it's also given by just starting with some microcanonical state and then acting with field operators on both sides. So,
Whatever you call field operators, but the whole
well, I
crux,
think you're fine with that work, right? They were just these spots. I mean,
in the quantum field theory, but not in the microphysical theory. In the microphysical theory, you do it with the O's, and the O's reduce entropy, phi's do not. So in the phi theory, you don't see that the thing is extracting entropy because you're creating a particle. But in the microphysical theory, you see that you're reducing entropy because you start recognizing that the phi that creates something behind the horizon is actually a projection operator.
no, fine, but sorry. From the CFT point of view, you had some microcanonical density matrix, and then you acted with a couple of primary operators, right?
Correct.
Right. Okay.
But the primary operators, when they get too close to the states that create the microcanonical state, they become things that reduce the entropy. By the way, when you say projection, there was a confusion that I had. So this is one of these subtle points. If you look at an OPE expansion, is it literally a projection operator, or is it the projection operator plus very tiny coefficients times things that might not be literally projecting it to zero? It dominantly looks like a projection operator. At least it reduces the entropy.
Okay. No. Thanks. Come on again.